Nakuishi hapa kamdia watu wakuja.
Hello,
Baraka wewe.
Huko ni zidi
Nakuanga prefect.
Hello? 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 Okay, I hope you're together and we can continue. Last time we left at hydrogen, carbonates, and hello? Let me see the charts whether we are together. Okay. There is an echo. Yes, I can detect it. We work on it. Hello? Hello? Let's work on the echo. Hello? The echo is too much. Just be patient. Sema nini? Hmm? Hello? 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 Zero, 100 to 0. Hello? 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 That is the echo. Hello? 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 I hope we are together now. We can continue. So let's continue from where we left last time. Sorry for the inconveniences. Welcome to our today's lesson. We've been looking at carbon and its compounds, and last time we went as far as carbonates and hydrogen carbonates. I did the introduction on carbonates and hydrogen carbonates, and we said these are salts of either metal ions or ammonium ions with the carbonate ions. We said the source of carbonate ions is when the carbon dioxide dissolves in water to form the weak dibasic carbonic acid. And this acid portrays or has got all the characteristics of an acid. So it reacts with either the metal ions or ammonium ions, and the corresponding carbonate salt is formed. We also managed to discuss on the one property of these carbonates, and that's how they react with acids, and so that they react with acids to form the corresponding metal salt, the carbon dioxide, and the water. However, we said there are some carbonates whose reaction will not go on to completion. And we gave examples of such reactions. We gave an example of lead-2 carbonate with sulfuric 6 acid, calcium carbonate with sulfuric 6 acid, which results to the insoluble salt, lead-2 sulfate and calcium sulfate, respectively, which are not soluble in water. So what happens? They form a coating, and this coat prevents any further reaction from taking place. We also mentioned an example of a reaction between the lead carbonate and the HCl, dilute hydrochloric acid, leads to the formation of lead-2 chloride, which is insoluble in cold water. So today, we are going to move on to the other property of the carbonates, and that is what happens when they are heated. Action of heat on carbonates and hydrogen carbonates. Action of heat on heat on carbonates and hydrogen carbonates. action of heat on carbonates and the hydrogen carbonates. That's where we are moving on from. Carbonates and hydrogen carbonates. What happens when they are heated? It's good to note that the action of heat on most of the salts depends on the location of the metal in the reactivity series. And the same case applies to the carbonate. The carbonates of the potassium and sodium. Potassium carbonate and sodium carbonate. These are the first two. The sodium, here we can see the whole board. Hope now you can see. The carbonates of potassium and sodium are hello, I hope we are together. I hope you can see from the chart. All carbonates, apart from this, the sodium carbonate and potassium carbonate, all the others that are below sodium in the reactivity series decomposes on heating. So these two are the ones that do not decompose on heating. These two, when heated, they don't change. They don't undergo any decomposition. But all other carbonates, any other carbonates below sodium in the reactivity series decomposes to give two products. One, the corresponding metal oxide, and two, carbon 4 oxide, and two, carbon 4 oxide. The general equation for this, can write it as metal carbonate, but note it is for those carbonates below sodium in the reactivity series. Any metal carbonate below sodium, when heated, decomposes to give the corresponding metal oxide and the carbon 4 oxide. Decomposes to give the metal carbonate, the metal oxide, sorry, and the corresponding carbon 4 oxide. For example, can have copper 2 carbonate. If copper is below sodium in the reactivity series, when heated, the corresponding metal oxide will be copper 2 oxide and carbon 4 oxide. In this case, the examiner always tests on the color changes, and especially on the flow diagram. The copper carbonate, copper 2 carbonate is green, copper 2 oxide is black in color. So these are the areas the examiner will draw a diagram. We are going to see one. Then indicates the copper carbonate or lead 2 carbonate or the zinc carbonate, and tells you to state and explain the observation. So with copper 2 carbonate, that is what will happen. It will decompose to copper 2 oxide and carbon 4 oxide. What about with lead 2 carbonates? It's another carbonate which undergoes some color changes on heating. Lead 2 carbonates, lead is below sodium in the reactivity series. So if heated, once heated, it undergoes thermal decomposition to give the corresponding metal oxide, which is the lead 2 oxide, and carbon 4 oxide, and carbon 4 oxide. This one is also accompanied with color changes. The lead 2 carbonate is white. The lead 2 oxide depends on the color, depends on whether it is hot or cold. This one is orange when hot and yellow when cold. Yellow when cold. So, if the diagram is drawn and you are told to state and explain the expected color changes, you should capture the two color changes. On heating, it changes from white to a solid, which is orange when hot and yellow when cold. Another commonly tested carbonate is the zinc carbonate. The zinc carbonate, on heating decomposes to the zinc carbonate. Once heated, decomposes to the zinc oxide and carbon 4 oxide. The zinc carbonate is a white solid, but zinc oxide color depends on whether hot or cold. This one forms a yellow solid when hot and a white solid when cold. This one forms a yellow solid when hot and white solid when cold. Diagrammatically, this is also a very common diagram in the exam. This is also how this concept of effects of heat on carbonate is tested. Mostly, the examiner will draw such kind of a diagram, a boiling tube, and the solid here can be either of the carbonates that we've discussed. The metal carbonate, maybe you can start with copper 2 carbonate, and then it is heated. There is heating that is taking place. The gas produced is allowed to pass through the lime water, the calcium hydroxide, the calcium hydroxide. So mostly this is how this area is tested, and also in the flow chart diagram. So here we have with us our test tube A and B, and in this one we have the calcium hydroxide solution, which is the lime water. We have the calcium hydroxide in the lime, which is lime water. So in such case, the examiner will tell you to state and explain the observations made when this copper 2 carbonate is heated. It's below sodium, so it will decompose to form copper 2 oxide and carbon 4 oxide. So what is the expected observation? This one you said is green. It decomposes to copper 2 oxide, which is black. So the changes are the green copper 2 carbonate changes to black copper 2 oxide. If it was zinc carbonate, the white zinc carbonate will change to a solid, which is orange, which is yellow when hot and white when cold. If it is lead 2 carbonate, the white lead 2 carbonate will change to a solid, which is orange when hot and yellow when cold. So it's good to be armed with those color changes. What observations will be made in the test tube? B. What observations will be made in the test tube labeled B? This is something we've covered on the test of carbon 4 oxide. I believe you can be able to give me some response on that. Someone is asking about the color of zinc carbonate. I've said it's white and it decomposes to form the zinc oxide, which is yellow when hot and white when cold. I've seen a response there on the observations that will be made in the test tube B, which is very correct. I've seen someone, Levin, talking about formation of white precipitate. That is okay. The other question you may find from that area is by use of a balanced chemical equation, explain the above observation. Now we are still in B. By use of a balanced chemical equation, explain the above observation. So use of a balanced chemical equation and still get some response. We've covered this in the course of our sessions. Maybe you can get some response. When zinc oxide is cold, does it mean that it returns to, the message is not complete, it changes. If it becomes cool, it changes to white. If you heat it, the white color changes to yellow. Yes, it depends on whether it is hot or cold. If it is hot, the color is yellow. If it is cold, the color is white. I'm still waiting. I'm still waiting. Which is this? Which is the? Someone is talking the green solid. The green solid is copper 2 carbonate. I have seen the response from what is very hot. That's when this gas that is formed here. The question was you explain by use of a balanced chemical equation. It is very correct. We have the carbon 4 oxide. Once it gets into contact with the lime water, calcium hydroxide, the product formed calcium carbonate, which is insoluble, and the water. And this is why you observe the white precipitate. Another question that can still be asked from that area is if it is allowed to pass through in excess. If this carbon 4 oxide is allowed to pass through the white precipitate in excess, what would be the expected observations? So if it is allowed to pass through in excess, a colorless solution is formed. The colorless solution is formed due to the formation of calcium hydrogen carbonate. The colorless solution is due to the formation of calcium hydrogen carbonate, which is soluble, and that's why you observe a colorless solution. That's why you observe a colorless solution. There is a carbonate that I've not mentioned here. The one I've talked about is about the metal carbonates. But when we were introducing on the carbonates, we say they can be from a metal or ammonium ion. So we can still have ammonium carbonate, and ammonia is nowhere in the reactivity cells. What happens if the ammonium carbonate is heated? It will decompose. The only two carbonates that will not decompose are potassium and sodium carbonate. So ammonium carbonate decomposes on heating, and it gives three products. These are the ammonia, the carbon dioxide, and water. So this is what happens if it is ammonium carbonate that is being heated. It decomposes ammonium carbonate and HCO3, and ammonium has a valency of 1, while carbonate has a valency of 2. So that is the correct chemical formula for ammonium carbonate. When heated, we get three products. One of them is the ammonia gas. The other one is the carbon dioxide, and the third product is water, which is in gaseous form because you're heating. It's good to note that ammonia is the only alkaline gas. So the gas produced here can be tested by moisturized red and blue litmus paper. The red changes to blue, while the blue remains blue. This indicates the presence of the ammonia gas, shows the presence of ammonia gas. Now that's about the carbonates. That's about the carbonates. We move on to hydrogen carbonates. Yes, I've seen Brighton responding to that. That one is okay. The response is good. Let's continue to the other category of the carbonates, and that is hydrogen carbonates. What happens when hydrogen carbonates are heated? What is the effect of the heat on hydrogen carbonates? If you remember what we said last time about the hydrogen carbonates, we mentioned those that exist, and we said potassium, sodium, and ammonium hydrogen carbonate exist as solids at room temperature. The other hydrogen carbonates that exist in solution form are the lithium, the calcium, and the magnesium hydrogen carbonates. All other hydrogen carbonates do not exist. And therefore, when we talk about the action of heat on hydrogen carbonates, we are talking about these hydrogen carbonates of the sodium, the potassium, the lithium, the calcium, and magnesium hydrogen carbonates. So with hydrogen carbonates, they all decompose on heating to give the metal carbonate, that is the first two, sodium and potassium hydrogen carbonate. Sodium hydrogen carbonate and potassium hydrogen carbonate. Remember the carbonates, we say they are stable. They will not decompose on heating. But these two, when are heated, they decompose to the corresponding metal carbonate. So the corresponding metal carbonate in this case is sodium carbonate. The other product is carbon 4 oxide, and the other product is water. Likewise to potassium hydrogen carbonate. The corresponding potassium carbonate, carbon 4 oxide, and water will be the product. So the general equation for these two will be metal hydrogen carbonate, metal hydrogen carbonate, decomposing on heating to give the corresponding metal carbonate, the carbon 4 oxide, and the water. This is for the two. So what about the others? The lithium hydrogen carbonate, the magnesium hydrogen carbonate, and the calcium hydrogen carbonate, which you are saying exist in aqueous form, in solution form, because they are below sodium in the reactivity series. They will decompose to the corresponding metal oxide, carbon 4 oxide, and what? Carbon 4 oxide and water. These two will decompose up to this point. So I can give an equation for the magnesium hydrogen carbonate, because these, the lithium, the calcium, and the magnesium hydrogen carbonate are below sodium in the reactivity series. So what will happen when magnesium hydrogen carbonate exists in the aqueous form, it is heated, will end up with the corresponding metal oxide, the carbon 4 oxide, and the water. Because once this one is converted to the metal carbonate, it's below sodium in the reactivity series. So on further heating, it will be decomposed to the corresponding metal oxide. So that's about the effect of heat on the carbonate and hydrogen carbonate. Is there any question so far? Okay, someone is requesting that I repeat on those hydrogen carbonates that do not exist. I repeat, I said with hydrogen carbonates, we have potassium hydrogen carbonate, and we have potassium hydrogen carbonate and sodium hydrogen carbonate, which exist as solids. We have lithium hydrogen carbonate, magnesium hydrogen carbonate, and calcium hydrogen carbonate, which exist in solution, So any other metal hydrogen carbonate does not exist. I hope I'm clear to the person who asked that question. If please repeat, since sodium hydrogen carbonate is soluble, should it not be aqueous? Yes, in presence of water, it will dissolve. It will exist in solution form. But in absence of water, it can be a solid. That is okay. It's a soluble salt. I think I've responded to most of the questions. There's someone is asking what happens when you heat ammonium carbonate in the presence of the moist blue and red litmus paper. I think I've explained that. I've said that ammonium carbonate decomposes on heating to give three products. And these three products are one, the ammonia gas, two, carbon dioxide, and three, water. The ammonia gas is the only gas that portrays the alkaline properties. So if a moist and red litmus paper are introduced to the boiling tube where ammonium carbonate is being heated, we expect some color changes. The red litmus paper changes to blue litmus paper, while the moist blue litmus paper remains blue. Larry, your statement is not complete. Not able to read all of it. We have lithium. We also have lithium. You can also add lithium there. Then from there, I think we'll move on to the next subtopic, and that is large-scale manufacture of sodium carbonate and sodium hydrogen carbonate. Large-scale manufacture of sodium carbonate and sodium hydrogen carbonate. This is our second last subtopic in this topic, and it's also a very highly examined area in exam. Large-scale manufacture of large-scale manufacture of sodium carbonate and sodium hydrogen carbonate. These are major substances that we use in our day-to-day life. Sodium carbonate is also referred to as soda ash. This sodium carbonate has got very major uses. One of them, it is used as a raw material in the glass and paper industry. It is used as a raw material in the glass and the paper industry. It is used as a raw material in the glass and the paper industry. Sodium carbonate is also highly used in the water treatment plants. It is highly used to treat water. Sodium carbonate is also used to make sodium silicate. And this sodium silicate is used to make detergent. And from these uses, you can see that sodium carbonate is highly used, and for this reason, it should be manufactured in large quantities, large amount. How do we get it in large quantities? How do we get it in large quantities? there are two ways through which this sodium carbonate can be manufactured in large quantities. One of them is extraction from trona, and two is the solving process. One of them, there are two ways that sodium carbonate can be obtained in large quantities. That's what we are referring to as the large scale manufacture. And this is through extracting it from trona. And the other method is through a method known as the solving process, which is highly tested in exam in form of flow chart. So I'll start with the first method of manufacturing sodium carbonate in large quantities, and that is extraction from trona. And that is extraction from trona. How can we get it through this method of extraction from trona? So sorry for the disruption. Let's continue. The first method of manufacturing sodium carbonate is through extraction from trona, and I've said the other one is through the solving process. So we start with the first one, that is trona, extraction from trona. So we need to know what is trona. Trona is a double salt. When we covered the topics on salt, we looked at the different types of salt, and one of the salt that we came up, one type of a salt continue. I've said that the first method of obtaining sodium carbonate is through extraction from trona. So we need to know what is trona. It's a double salt. And this double salt contains two different anions, the carbonate and the hydrogen carbonate, and it is also hydrated. It contains water of crystallization. So trona is a double salt that contains in it the sodium carbonate, then sodium hydrogen carbonate, and it is hydrated. It contains two molecules of water of crystallization. So from this, we can be able to get our sodium carbonate, which is our interest, which you have highlighted its uses as quite a lot. So where is this trona found? This trona is found in salty lakes, most of them in the Rift Valley regions, for example, the Lake Magadi. So within the lake, we have the solid trona. We have the solid trona within the salty lake. We have the solid trona, which is the sodium carbonate, sodium hydrogen carbonate, but it is hydrated. Within the lake, we also have small amount of sodium chloride? That's a question I've seen one of you asking. After explanation, I'll have answered that question. So how is it obtained from this mixture? It can be dug by use of buckets, dredges. Trona is dug by use of bucket dredges, and after it has been dug, it is taken to the washery. I can explain that in form a simplified flow chart. We have the solid trona in the lake, and this one is in solid form, but it's in mixed with the sodium chloride. So what happens? It is first dug by use of the bucket dredges. It is dug by the bucket dredges. From here, it is taken to the washery. Why in the washery we have in water. It is taken to the washery, whereby it is washed in water to remove the mud and the small rocks. Here it is washed, and the main reason of washing is to remove the mud and the small rocks. After being washed, it's now wet. It is centrifuged. It is taken to a centrifuge. Centrifuge means it's a means of, or it's a device of separating various solids based on their size, based on their density or mass. So we saw it is in solid form. So the various sizes will be centrifuged to remove water and also to purify it further. This one helps to remove water and also to purify it further. After centrifuging it, we now have with us our wet sodium carbonate, sodium hydrogen carbonate. We have with us our wet trona ambayo tulisema ni sodium carbonate, sodium hydrogen carbonate, and it is hydrated in solid form. So this one is then heated. It is strongly heated. And what happens from the effects of heat on the sodium hydrogen carbonate? We started with sodium carbonate. Ambayo tulisema if you heat it, it will not decompose. We went on to sodium hydrogen carbonate, which is said when you heat it, it decomposes to the sodium carbonate, the carbon 4 oxide, and water. So when all this is heated, the end result is our interest, which is the sodium carbonate, the carbon 4 oxide, and water. The carbonate, the carbon 4 oxide, and water. Due to strong heating, this sodium carbonate that is obtained is allowed to undergo cooling. It is grounded into small pieces. It undergoes sieving, and then it is bagged. It is sieved, and then it is put in bags ready for the transportation to the customers. So extraction from trona is as simple as that. You only need to know what is trona. We started by saying it's a double salt which contains two different anions. The two different anions are the carbonates and the hydrogen carbonates, where it is found mostly in the salty lakes, where we only have the inlets and no outlets. And how it can be obtained. How it can be obtained. We've discussed, we've mentioned that it can be obtained through two ways. The first one is extraction from trona, and the second one is the Solvi process. We are through with extraction from trona. I've tried to simplify it in form of flowchart, a simplified flowchart. This is the trona from the lake. It is dug by use of the bucket dredges, and we take it to the washery. In the washery, we have got water whereby we wash it, na tunaondoa the small rocks, na tunaondoa the mud. From there, our wet trona is centrifuged. It is separated according to the size, the density, or the volume. And with this wet trona, we heat it strongly, where the sodium hydrogen carbonate will decompose to the sodium carbonate, and this sodium carbonate is allowed to undergo cooling, and on cooling, it is clouded, sieved, and then put in bags and transported to the customers for use in the glass making, the paper industries, the water treatment, and to manufacture the sodium silicate. That is the first method of extracting of manufacturing sodium carbonate in large scale extraction from trona. Don't know whether there is any question from that area before I move on to the Solvi process. Someone is complaining about the board. I hope there is an improvement now. So let's continue to the next method of I can't probably could wait. I hope now there's an improvement. We move on to the second method of preparing sodium carbonate in large quantities. The second method of preparing sodium carbonate in large quantities, and this method is known as the Solvi process. The Solvi process, which is a very fertile ground in exam. This is very important. I hope the board is now clear. Someone is identifying himself as J. I've worked on it. I hope it is now clear. Thank you. We continue with the second method of manufacturing sodium carbonate in large quantities. And this method is called the Solvi process. This method is known as the Solvi process. We are going to look at it in details. The Solvi process. The Solvi process is our next topic. The Solvi process is our next subtopic, and if the trona is not available, then sodium carbonate or sodium hydrogen carbonate can be manufactured by the Solvi process. It can be manufactured through sodium carbonate or sodium hydrogen carbonate is not available. it's possible to manufacture it through a process called the Solvi process. The most important thing to know about this area is the raw materials. The raw materials for the Solvi process. The raw materials for these processes are: one, sodium chloride, the sodium chloride, calcium carbonate, the raw materials for this process are: one, the sodium chloride, two, calcium carbonate, calcium carbonate. The third one is coke. We came across it when we were discussing the amorphous form of carbonate, amorphous form of carbon, and coke was one of them. And we said its major use is as a raw material in the Solvi process. That's why we are mentioning it here. The other raw material that is used in the Solvi process is the ammonia. And we also need to set up the Solvi process where there is enough source of water. So these are the major raw materials for the Solvi process: the sodium chloride, the calcium carbonate, the coke, the ammonia, and the water. Now, these raw materials are very readily available, and they are cheap, and they are recycled, making the Solvi process one of the most economical and efficient process due to the availability of these raw materials and the cost. And they are also recycled. As you are going to see, everything here is going to be recycled apart from only one, which has got major uses. So what are the steps that these raw materials undergoes until we get large quantities? What are the steps or the flow chart on the Solvi process? Most of the flow diagram are different, but once you have the concept, you can easily digest it, interpret it, and respond to the examiner's question. We have the flow chart in simplified form, as I'm going to sketch it on the board. The first one is a chamber called the first absorption tower. First step is where we have the, we call it the chamber one, and chamber one is the first absorption tower. You can write it one, then you write key somewhere and refer to it as the first absorption tower. We have the second chamber, and this second chamber is the ammonia generator. It is the source of the ammonia. It's the ammonia source. We have the third chamber, and in this third chamber, we refer to it as the carbonator. Hope you are writing the keys. We have the carbonator. We have the fourth one, and the fourth chamber is the kiln, where we have the coke and the limestone. We have the kiln, whereby we have the coke, we have the limestone. So we'll discuss in details what happens in each of these. The first one we said is the first absorption tower. So in this first absorption tower, we have the sodium chloride concentrated. Concentrated sodium chloride is also called brine. So in this first chamber, we are bringing in brine, concentrated sodium chloride. The second one, we said, is the source of ammonia. It is the ammonia generator. So this ammonia from the second chamber is fed into the first absorption tower, where it is meeting with sodium chloride, which is brine concentrated. So we have in sodium chloride and we have in the ammonia gas from the ammonia generator. Once these two mix, they form what we call ammoniacal brine. They form what we call the ammoniacal brine. Just as the materials are, it's ammonia and brine, which is concentrated. Is it ammonia or ammonium? It's ammonia, ammonia gas, ammonia generator. So ammonia and sodium chloride, once they mix, that's when they form the ammoniacal brine. So it's the ammonia generator, not ammonium generator. So the ammoniacal brine is fed into the third chamber, which is said is the carbonator. I'll discuss on the structure of the carbonator later on and see how inside this carbonator are the structures of it. So, and that's why we get the name solvent from the structure of the carbonator. So this ammoniacal brine is fed from the first absorption tower to the carbonator through up, huko juu. It is fed from the top of the carbonator. The ammoniacal brine is fed into the solvent. Inside the carbonator, we have the solvent towers. And I've discussed the purpose of those solvent towers. We are going to draw them. It is to allow the slow downward of this ammoniacal brine by gravity, and they also increases the surface area for the reaction to take place. We had the fourth chamber here, which we referred to as the kiln. In the kiln, the coke is heated and the limestone, calcium carbonate are heated. We are going to see the equations for that and how they are used. But once they are heated, in each of them, they generate carbon dioxide. Carbon dioxide will be formed. And this carbon dioxide that will be formed will be fed into the carbonator from the bottom. It will be taken into the carbonator kutoka chini. So we have the carbon dioxide kutoka chini ya carbonator na tuko na ammoniacal brine kutoka juu ya the carbonator. So what happens? When the ammonia and the sodium chloride are combining to form the ammoniacal brine, the process is exothermic. Exothermic means a lot of heat is evolved. A lot of heat is given out because the process is exothermic. And for this reason, the setup of the solving process should be close to a source of reliable water, to a reliable source of water. This water will help to cool down the high temperatures. So what happens when the ammoniacal brine and the carbon dioxide meet inside the carbonator? This is very important, the equation in the carbonator. And because of space, allow me to delete this because you've understood the various chambers. So the next is the equations that takes place in the carbonator, which I believe I need to write. So in the carbonator, we brought in carbon dioxide kutoka chini, and we brought in the ammoniacal brine, which is a mixture of ammonia and brine, sodium chloride concentrated. So when they meet, the aqueous ammonia from the ammoniacal brine reacts with carbon dioxide that we fed from the bottom of the carbonator. And once they react, we end up with ammonium hydrogen carbonate. I repeat that. We are in the carbonator. What equations takes place in the carbonator? And this is where examiner mostly dwells in. The equations are the reactions that takes place in the carbonator. In the carbonator, nimeelezea kutoka juu, we are bringing in the ammoniacal brine, which is a mixture of ammonia and concentrated sodium chloride. From the bottom of the carbonator, we are bringing in carbon dioxide. So this is the first reaction that takes place in the carbonator. The ammonia from the ammoniacal brine, it is aqueous, and it reacts with the carbon dioxide from the kiln. And we said this process needs to be cooled down by water. So there is presence of water. And when these three combines, we end up with ammonium hydrogen carbonate. We end up with ammonium hydrogen carbonate. That is the first reaction that takes place in the carbonator. Ammonium hydrogen carbonate. Still within the carbonator, this ammonium hydrogen carbonate. There's someone who is writing a chat. Just allow me. Is it ammonia? I responded to that. Don't think there's. I can see another one. Let me just. I think it is different people who are asking the same. It's ammonia. So this ammonium hydrogen carbonate reacts with the sodium chloride. Remember, we brought in the ammoniacal brine, ambayo nilisema ni mixture of the sodium chloride and ammonia. So the ammonia has first reacted with carbon dioxide to form the ammonium hydrogen carbonate. This ammonium hydrogen carbonate in turn react with the sodium chloride. And what is the end result? Sodium hydrogen chloride and ammonium chloride. So this is the second equation that takes place in the carbonator. This ammonium hydrogen carbonate, this ammonium hydrogen carbonate reacts with the sodium chloride, the concentrated sodium chloride from the ammoniacal brine, and the end result is sodium hydrogen carbonate and ammonium chloride and ammonium chloride. Note the physical state, they are different. So we have now with us sodium hydrogen carbonate and ammonium chloride. Sodium hydrogen carbonate is sparingly soluble in this reaction medium, and so it precipitates out. Sodium hydrogen carbonate is sparingly soluble in this reaction medium, and so it precipitates out, and it is recovered by filtration process. It is filtered as a precipitate, while ammonium chloride remains in the solution. While ammonium chloride remains in the solution. Once it has been recovered through filtration, it is dried and heated, and on heating, we've learned from effects of heat on hydrogen carbonate, it decomposes to the sodium carbonate, carbon dioxide, and water. So after filtering, the sodium hydrogen carbonate is strongly heated in the iron tubes. and on heating it strongly, we've learned that it will decompose to the sodium carbonate, which is our interest. Other byproducts are carbon 4 oxide and water. Carbon 4 oxide and water. So this carbon 4 oxide is recycled. It's taken back to the carbonator from the bottom. And in the kiln, we had the two substances. One of them was coke and the other one was limestone. Limestone is calcium carbonate. So we are now, this is the equation that takes place in the carbonator. In exam, you may be asked to write the whole equation, which we are going to write, because it entails ammonia, carbon 4 oxide, and water to form the ammonium hydrogen carbonate, which is reacted with sodium chloride. So tunaweza ongezea sodium chloride here, and then on this side we end up with sodium hydrogen carbonate and the ammonium chloride. It can be combined. You can combine the whole equation or you can write it in straight form. So let's go back to the carbon 4 oxide. We said the carbon 4 oxide produced here inarudishwa back to the carbonator. We now move on to the kiln where we had coke and limestone. So the coke is amorphous carbon. Amorphous carbon, if you heat it in controlled amount of air, we saw that carbon in excess amount of air, carbon 4 oxide will be formed. There was also limestone, calcium carbonate. On heating it, we've just discussed the effects of heat on carbonate. It will decompose to calcium oxide, the corresponding metal oxide, and carbon 4 oxide. Hii tunaipeleka kwa carbonator. What about this calcium oxide? This calcium oxide is reacted with water in a slaker. It undergoes a process called slaking. This calcium oxide is reacted with water in a slaker. And this leads to the formation of the calcium hydroxide, which is referred to as the slake line. Hence, the whole process is referred to as the slaking. This calcium hydroxide, remember in the equation in the carbonator, tulipata sodium carbonate na tukapata ammonium. Tulipata sodium hydrogen carbonate na tukapata ammonium chloride. Sodium hydrogen carbonate ndio ile to decompose, tukapata sodium carbonate. What about ammonium chloride? Ndio hii inakuja ina react na the calcium oxide. Calcium oxide imetoka wapi? Imetoka kwa killing on decomposing the calcium carbonate. So what happens when this calcium hydroxide reacts with the ammonium chloride that was formed as the second reaction in the carbonator? After carrying out the precipitation, after carrying out filtration, tulipata hii as the filtrate. Tukapata sodium hydrogen carbonate as the precipitate na tukaidecompose. Sasa tulibaki na the filtrate as ammonium chloride. Ndio hii tunapeleka kwa slaker whereby it's reacted, whereby we are first getting the calcium oxide from the kiln, react it with water in the slaker to form the slake line, which is reacted with ammonium chloride. What happens? What are the end result? The end result here are a salt known as calcium chloride, a salt by the name calcium chloride. The other product here is the ammonia gas and water. The other product are water and the ammonia gas. To balance the equation, you can multiply there by 2. and you can multiply there by 2. So what happens to the water? It is recycled. We say this process should be located where there is enough source of water to cool down the exothermic reaction during the formation of ammoniacal brine. Ammonia, it is taken to the ammonia generator, whereby it's fed to the first absorption tower, mixes with sodium chloride to form the ammoniacal brine. So from here, you can see that every byproduct is recycled. The only byproduct which is not recycled, which is not reused, is calcium chloride, which has got so many use, especially when it is anhydrous. It is used as a drying agent. So entirely, that is the solving process, which the examiner will twist the flowchart, but it is a highly tested area in exam, especially in the flowchart diagram. So the only thing left is to subject ourselves. Someone is telling me to repeat from carbon 4 oxide and the ammoniacal brine. I will repeat, there's no problem. I said, what are the two products that are recycled? We have carbon 4 oxide, we have ammonia, we even have water. All those are recycled. So someone has requested I repeat from carbon 4 oxide and ammonia. I think he wants us to repeat what goes on in the carbonator. Carbonator, nilisema from the top, we are allowing in the ammoniacal brine. And ammoniacal brine, I explained and I said it's a mixture of the concentrated sodium chloride and the ammonia. So what happens? The ammonia in the ammoniacal brine, it is aqueous, maji, react with carbon 4 oxide. This one is from the killing, and the product formed is one, ammonium hydrogen carbonate. Ammonium hydrogen carbonate. This ammonium hydrogen carbonate, this is the first step, reacts with the sodium chloride from the ammoniacal brine. So all this inaanzia kutoka kwa ammoniacal brine ambayo tulisema ni mchanganyiko. It's a mixture of ammonia na concentrated sodium chloride. So ammonia kwanza ina react na carbon 4 oxide from the carbonator in a form ammonium hydrogen carbonate. That ammonium hydrogen carbonate in a react na the sodium chloride, ndio hii concentrated sodium chloride, na hapa ndipo tunapata sodium hydrogen carbonate, sodium hydrogen carbonate, which we said is sparingly soluble in this reaction medium, so it is recovered through the filtration and ammonium chloride. I said you can even combine the two, which all this can be combined into one equation, whereby we have ammonia gas tuko na sodium chloride, hizi mbili ndizo tunaita ammoniacal brine. The process is exothermic. We need to cool down by water. And what are the end results? The end result will be this one, the sodium hydrogen carbonate and the ammonium chloride. But this one now are taking place step by step. Hii ina take place step by step. Hii nime combine the whole equation. This one we said is sparingly soluble, so you carry out filtration and you get your precipitate as sodium hydrogen carbonate, and you get your filtrate as ammonium chloride. This one is the one we are heating and it is decomposing And once it decomposes, we get sodium carbonate, which is what we want in large quantities. We also get carbon dioxide, which is recycled. We also get water, which is recycled. This ammonium chloride is also not thrown away. We go back to the kiln, tulikuwa na limestone, calcium carbonate, ambayo on heating it form calcium oxide, which was leaked. Water was reacted with it to form calcium hydroxide. And this calcium hydroxide, once reacted with ammonium chloride, gave us calcium chloride, gave us ammonia, and gave us water, which are still recycled. This calcium chloride is not recycled, but it has got major uses. It has got a lot of uses, as one of them being a drying agent. Let's put to one or two charts. Does ammonium hydrogen carbonate exist in the carbonator? You've said it's in aqueous, but not so in the action. Ammonium hydrogen carbonate. Ammonium is not a metal. When I was talking about action of it on metal, I was talking about those that are in form of metal. So in this case, ammonium hydrogen carbonate depends whether there is moisture or not. All sorts of ammonia will be soluble. So if there is water, it will be aqueous. If there is absence of water, itakuwa in solid state. So we were told that water is not a raw material. I think I said one of the major raw material, we mentioned where should this site be located. It's where there is enough source of water. I think it's one. It's required to calm down the high temperatures. Please repeat about the types of hydrogen carbonates. Someone has taken me back to the types of hydrogen carbonate, which does the process of fractional crystallization. Actually, that is it. I have avoided to use the word fractional crystallization because you've not covered this in form 2. But this process, sodium hydrogen carbonate and ammonium chloride. Remember, under the topics of salt, we said all sorts of sodium, potassium, and ammonium are soluble in water. It's only that their solubility, and I said medium, in this reaction medium, this one is less soluble, or this one is highly soluble. So this one will exist as solid, or this one will exist in solution. And that process of separating two or more soluble salts in the same solvent is called fractional crystallization process. So you are correct when you talk of fractional crystallization process. That is okay. I think that is the same question that I've responded to. The other one, naona kama zinajirudia. So if there's no question, the only thing that we've not done on this area is subjecting ourselves to so many flowcharts of the solving process. There are so many in the top notch, book 2, and I'll request you to visit your top notch book 2. There are so many questions on the flowchart and especially on the solving process. So kindly ensure that you visit those questions, you try to answer them. That which will have an issue, we'll look at it later on. So if there's no question, I wish to stop at that. Thank you for your patience and your active participation.